Hello, friends. Today, we'll explore the story of stars arriving from the depths of the universe. Billions of years ago, deep within the cosmos, a faint signal of light emerged in the dark void. This light was the result of processes such as the fusion of subatomic particles, the movements of molecular clouds, and the release of energy. According to modern cosmology, this event took place in the universe's earliest moments, laying the foundation for the stars, galaxies, and planetary systems we see today. Let's dive into the process of star formation, their evolution, explosions, and their roles in the cosmos. The life of a star begins within vast molecular clouds. These clouds are primarily made up of basic elements like hydrogen and helium, and they also contain heavier elements released into the universe by past supernova explosions. Gravity gradually pulls these particles together, increasing the density. When the temperature and pressure in the core exceed a certain threshold, reaching roughly 15 million Kelvin, nuclear fusion ignites. In this process, hydrogen atoms fuse into helium through nuclear reactions, releasing a tremendous amount of energy. This energy counteracts the star's own gravity, allowing it to become a stable energy source for a long time. The life stages of stars largely depend on their mass. In medium-mass stars like our Sun, hydrogen continues to serve as fuel. When the fuel is exhausted, the star expands its outer layers and enters the red giant phase. In this stage, the star grows so large that it can have devastating effects on its surrounding planetary systems. Eventually, it sheds its outer layers into space and transforms its core into a dense white dwarf. On the other hand, stars about 20 times larger than the Sun undergo nuclear fusion much more rapidly in their cores, which means their lifespans are considerably shorter. While these massive stars convert hundreds of millions of tons of hydrogen into helium every second, low-mass red dwarfs continue to shine steadily for much longer periods. The final moments of high-mass stars are remarkably dramatic. The buildup of iron in their cores halts nuclear fusion, allowing gravity to take over, and the star explodes in a violent event known as a supernova. This explosion can be so powerful that in some cases, it outshines the combined light of all the stars in an entire galaxy. For example, the Crab Nebula, recorded by Chinese astronomers in 1054, is a stunning example of a supernova remnant. During these explosions, heavy elements like gold, platinum, and uranium are scattered throughout the universe. The ring you wear, or even the iron in your body, carries traces of the materials forged in these cosmic events. After a supernova, the remaining core transforms into different objects depending on its mass. Cores that exceed about 1.4 times the mass of the Sun become neutron stars, city-sized objects of incredible density, where a small amount of matter can equal billions of tons. Some neutron stars, with their strong magnetic fields and rapid rotations, emit regular radio waves. These are known as pulsars. If the core's mass exceeds roughly 3 times that of the Sun, the star collapses into a black hole. Black holes warp space-time to such an extreme degree that not even light can escape their grasp. In 2019, the Event Horizon Telescope captured the first direct images of black holes, allowing us to test the theory of general relativity. For instance, the stars orbiting Sagittarius A star at the center of our Milky Way provide crucial data on how Einstein's theories work in practice. Stars are not merely physical objects. They are symbols that have left deep marks on human culture. The ancient Egyptians linked the rising of Sirius with the annual flooding of the Nile, And while the Vikings relied on the North Star for navigation, today astrology and horoscope readings continue to highlight the influence of the stars. Scientific research is constantly developing new methods to understand the nature of stars. With the James Webb Space Telescope coming online in 2022, we gained the ability to directly observe the star formation processes of the early universe. This telescope has allowed us to study light sources from about 300 million years after the Big Bang, and in systems like TRAPPIST-1, traces of water and organic molecules have been detected, clues to the conditions necessary for life. The light emitted by a star tells us about its chemical composition, surface temperature, and motion. Through spectral analysis, we examine the lines in its spectrum to determine element distributions. Stars with blue spectra indicate high temperatures and youth, while those with red spectra suggest lower temperatures and more advanced evolutionary stages. Additionally, Doppler shift analysis lets us calculate a star's velocity relative to Earth, a crucial tool in discovering exoplanets and studying the movements between galaxies. In the 1920s, Henrietta Leavitt's work revealed the relationship between the brightness cycles of Cepheid variable stars and their distances. These measurements played a major role in Edwin Hubble's development of the theory of an expanding universe, helping us calculate cosmic distances and understand the dynamics of the cosmos. The energy production mechanism of stars holds the promise of being replicated in laboratory conditions. Nuclear fusion research seeks to mimic the processes occurring in the cores of stars. The ITER project in France is one of the largest experiments in this field. ITER aims to recreate the core conditions of the Sun on a laboratory scale and produce clean, unlimited energy. Although a definitive energy gain has not yet been achieved experimentally, the first plasma tests are planned for 2035. Such efforts could play a vital role in meeting our future energy needs with sustainable sources. When you gaze up at the night sky, every star is more than just a point of light. It's a repository of information from the past. The light from a star reflects cosmic events from millions of years ago. For example, the view of the Andromeda Galaxy dates back approximately 2.5 million years, while the light from the Orion constellation is over 1,000 years old. This phenomenon helps us understand how information is transmitted and cosmic evolution unfolds on a universal timescale. The life cycle of stars encompasses stages of formation, evolution, explosion, and remnants. Each explosion creates and disperses new elements into the universe, contributing to the formation of planets, star systems, and ultimately, life. We, composed of essential elements like carbon, nitrogen, and oxygen, are part of this cosmic cycle. As Carl Sagan famously said, "We are made of stardust," highlighting the universe's ongoing process of self-discovery and renewal. Friends, in this video, we've examined the evolutionary processes of stars and their roles in the universe from a scientific perspective, while also shedding light on the profound impact cosmic events have on humanity. Advances in astronomy and astrophysics not only help us understand the building blocks of the universe, but also pave the way for future breakthroughs in energy production, planet exploration, and a deeper understanding of universal dynamics. Thus, we continue to uncover the secrets of the universe together. Remember, every patch of the sky you gaze upon holds a story waiting to be told.